Yeah, so we did a bunch of stuff with formats principle last time, but today we'll get a little bit more into detail on formats principle. We'll discuss optical imaging, some other effects of formats principle like mirages. And then we'll even talk about how we can use it to design telescope mirrors, which might be of interest to some of you that are in astronomy track. And we'll also start to think about how lenses work both in principle and in practice, how we design them, and or how we can write down the equations for the lens objects and image points in a lens. Okay, so we have a few things to do, but before I do, we just ask if there are any questions from last class, and also just a quick reminder that there are some homeworks that are due today. So I think there's some homeworks for this class. There's homework for 1661 as well that are due today. So
homework due is that homework 1?
Homework 1. Yeah, that's right.
Yeah, so yeah, I submitted the homework. What does my grades appear before that? They're not.
I might have graded it already.
Oh,
yeah. So but yeah, anyway. Okay. Alrighty. So I don't have any more questions, then let's get straight to the discussion. So our again. It's incapable of adjusting this, right? Sorry. So we talked about Fermat's principle of reciprocity or reversibility. I gave you an illustration of that. So suppose I have a point A, and this goes back to your one of the experiments you did in the lab. And I said that if I were to look at a ray that goes in, and this is the normal so this is the angle theta I, which is the incident angle. Let's consider some point, say B prime, inside the glass. We know from, let's get a little bit out here. And we know that this point, is going to, because of the law of refraction, we know that that's the least time point to that. We've already proven that. And now we can extend this out to this point over here and go to some point B over here. Okay. Now, what I can say from the principle of reversibility is that by simply reversing the rays, I know that this must be an angle theta as well. Whereas with Snell's law, you would have to derive that by considering the refraction of the two interfaces. Doesn't seem like a big problem here. It's only two interfaces, but you can imagine if I started making this problem more complicated, it would be a lot of different equations to solve and figure out what the angles are at each point. Okay. Or another way to say that is if I were to extend this initial ray over here to the point A prime, for example, from A, then we know that in the absence of the glass, A prime would be the point that it would get to because that's a straight line, right? And so it takes a certain amount of time to go from A to A prime, and we know reversing it, it would have to come back to the point A. And what I'm saying now is that the point B is equivalent to that point A prime, except that it has gone through the glass. Okay. And therefore, by reversibility, if I again go back the same way, everything must follow those same angles. Okay, just a small little thing, but now let's talk about, so this is the principle of reversibility. So we use a lot as we discuss imaging and things like that. Okay, let's discuss now imaging systems. What do I mean by an imaging system? Okay. Well, it makes sense that if I have an object point, let's call it O, and I have some, some system of optics, something in here, we don't know what it is. I just said this is an imaging system. It could be one lens, two lenses, mirrors, whatever it is. Okay, so it's a black box. And the point is that I say that this black box creates an image at the point I, and here I've drawn it around an optical axis. So you can kind of think of the imaging system as being symmetric around this optical axis. Imagine that if I rotated everything around that optical axis, everything would remain symmetric, which is pretty standard for most optical systems. Well, the idea is that for an imaging system, of course, we know from every object, there's an infinite set of rays that come out from this object, right? Because we can think of the object as like a point source. So that means that there are spherical waves coming out from that point source. And when we draw the normal to the spherical waves, that will be an infinite set of rays which are directed radially outward from that point source. Well, the definition of an imaging system is that all of these rays, that infinite set of rays coming from the object, every single one of them must reach the image point. Okay? That is the definition of perfect imaging or stigmatic imaging, as it is called, stigmatic imaging. And O and I are referred to as conjugate points. Okay? And the reason for that is from the principle of reversibility or Fermat's principle. Well, first of all, let's see what Fermat's principle says about the rays going from the object O to the image point I. Okay. Well, by Fermat's principle, a ray that goes through the system from O to I must follow the least amount of time, right? The path of least time or optical path length. Yeah. Which means that if all rays, every single ray takes the least amount of time to go from O to I, right? By definition, then all of them must take the same amount of time. Agreed? Because they all follow the least time path. No matter what angle, height, etc., they must somehow, after going through the optical system, still take the same amount of time to reach the point I. So we see that for an imaging system, every ray that goes through the imaging system must take the same amount of time, which also by definition is also the least amount of time to go from the point O to the point I. Okay. So an object and the conjugate points or stigmatic imaging, these 2 points are such that every ray takes the same amount of time to go from O to I. Everybody okay with this definition? We'll use it a lot. So it's important that you're, Howard first. Sorry. Sorry, Howard first.
I don't know if I understand how they all go the same at the same time.
It looks like they can't, right?
Yeah.
So you have to manipulate the ray's path length, optical path length, such that they end up taking the same amount of time. I'll give you an example very short.
Okay.
Go ahead.
Yeah. So when I was some examples from chemistry. So it's really want to image some in the molecular level that typically breaks diffraction limits, and then they have to use the time resolution, and then it's not equal. And then in that case, it's not equal time because of the diffraction limits. We can.
No, that's separate. That's different. That's not the same. We can talk about it outside class. Okay. Okay. All right. So now that we have this ray optical picture that everything must take the same amount of time, ask Howard asks, how is that possible? Right? I mean, I take the point O and the point I. This ray clearly takes the least amount of time in air because it's going right through from O to I in a straight line. Okay. So that is my least amount of time. So if I want a ray that is going this way to make it to I, well, first of all, I have to bend it clearly. So we know one way to bend it. We can use a prism, little piece of glass over there to bend it. Okay, we have seen that in your class or any piece of glass really will do, right? We'll bend that ray and it will reach the point I. Obviously, that increases the time slightly, right? Because well, first of all, the time is long compared to the central ray. Okay, but we have now made it at least go to the point I in some amount of time. And similarly, I could take a ray that goes like this. I could add a little piece of glass here. Sorry, I'm just going to, this is not a great drawing, but you get the idea. Okay? But clearly, somehow I have to delay the ray that goes through the center by a lot to make it go in the same amount of time. So I add a really thick piece of glass over here. Okay? And we know now the optical path length or the time that it takes for the central ray is going to be much delayed because it goes through this medium with refractive index n. Okay, so all of these, let's say, are made of the same refractive index. Well, in the infinite limit of doing this for every single ray, right, we're going to get something that looks like a lens. Okay? So that's the central concept of a lens, really. Okay? That's what it's doing. It's delaying the optical path length along the axis and sufficiently modifying the path length along off-axis rays, okay, so as to make them all bend and reach the image point at the same time. Okay, so that's for a lens. Okay, we can also do this with reflectors or mirrors. Okay, so now I'm going to give an example, as I promised, from astronomy. Okay. So what I have is, I have rays from a distant star. They're all coming. Remember, as the object gets further and further away, the waves of the wavefronts from that object are going to be planar. Okay, so all the rays here are basically parallel to each other. Okay. Let's say that I want to focus all these rays to a point, call that the focal point of the mirror. Okay. And I want all these rays to focus to this one point over here from some reflecting surface. Okay. So the ray goes here and then it reflects back from this point. Okay, I call this point usually the vertex of the mirror. You can just think of that as the point which is symmetric, has a symmetry point around which you can rotate the whole object, the mirror. Okay. Okay, so now I draw some coordinates. Okay. I'm going to call this the origin, really. This is like the origin. And this is the x-axis. And this is the y-axis. And any point over here on the surface of the mirror, let's call this point A, has a coordinate x, 1. Okay? All right, and I'm going to call the distance from F to V as the focal distance, which is F. Okay. And now we can see that this ray over here takes a distance F and then back here F. So let's call this ray 1 and this is ray 2. And now in this medium, this is all air because this is the reflector, not a refractor. Maybe I should, so the back of this is basically, this. There's no propagation light going through that region. Okay? So everything is just reflected at that interface. Okay? So this distance here is 2f, so ray 1 has a distance or time 2f, of course, divided by the velocity, but we can neglect that. Okay? We're just going to take the optical path length. Okay? So optical path length here is 2f. And here, that guy over here, well, this distance is f minus x, right? Because this is just x. And I now need to find out what this extra path length over here is. Okay. different coordinate system. Yeah. Okay. Sorry about that. I'm going to redraw the coordinates. Everything is correct. But coordinates are slightly different. So my coordinate axis, which I took some reason centered here, rethink what I did it this way, but it doesn't matter. Let's just get to this. So this is still y, this is still x, but I took the origin to be that point over there, v, as I call that. Origin or vertex, okay, all right, over here. And this is still that line over there. This is still the point F. Okay, that's all fine. All right. And this distance over here. Oh, okay, so this distance over here is x. Okay, from the origin, right? It's still a distance x. And this distance, which was previously, this was f. So this distance is now f minus x. And now this distance, this height above the axis for this point A is y. Okay. So we know that the total distance that this ray takes going from this point to here back down here, ray 2, is f minus x plus square root, right? We need this hypotenuse over here, which is just f minus x the whole square plus y. Okay. And these two rays must take the same amount of time if you are to form an image at the point F. So I equate everything to F equals F minus X plus square root F minus X, the whole squared plus Y squared. So it's pretty straightforward to do the algebra. What you do is you write this as F equals, or F plus X equals square root F minus X, the whole squared plus Y squared. Now square both sides. Okay, and simplify, and the end result, I'll just write the end result, is x equals y squared divided by 4. Okay, and that is the equation of a parabola, okay, which is around the x-axis. All right, so this equation, which is that of a parabola, tells us that for perfect imaging from a reflector, what we want is a parabola. Paraboloidal mirror. Of course, when you rotate it around the x-axis, because again we want everything to be symmetric around that axis, you'll get a paraboloid. Okay, and that's actually how telescope mirrors are made. So this is one of the things that you'll see, and many other applications of this. If you take in the old days, or even now, I guess, when you have an LED bulb and you want to project it into a collimated light, you put the bulb right at the focus of a paraboloid metal mirror, and you'll get a uniform illumination, for example, a headlight, and other kinds of illumination, like a microscope, etc., camera, projectors. All of these things can end up using this paraboloidal mirrors. Okay, so that gives us, again, by reversibility, like I was saying, this is, if you have an object far away, you get an image here. Well, similarly, if I have an object here, like an LED bulb or some other bulb here, that's going to give rise to rays of light coming out in parallel from this object. Okay, so those are two applications already for the Fermat's principle. One is a lens. Here it's more like a transmitting geometry. We go from O to I. By the way, we can ask, what shape should these surfaces be? Okay, we can do the same kind of thing that I just did here. I'll do that in a minute. It's called a Cartesian oval or Cartesian surface. It's like an ellipse. All right. So these surfaces here should be ellipsoidal for this refraction to occur from this point O to the point I to get exactly by the same argument, like exactly how we did this surface. We'll see that in a minute. I'll show you the equation. Again, it's not something that we'll discuss very often, as I'll explain for practical reasons. But before I go ahead, any questions on this paraboloidal mirror and how we derive? Please note the approach that I took calculating these rays. Like there might be a homework problem, maybe an exam problem, where you're asked to do this for a different type of geometry. Okay.
Yes. Sorry. So are in the here are we just treating the surface as the arc of the circle?
This surface, as we just derived, is the arc of a parabola.
Oh,
Yeah, obviously, we need an infinite parabola for all the infinite number of rays. And as you know, we can't make everything infinite, so but very large. You know, the larger it is, the better it's going to be at capturing all the rays from a star, for example.
Yeah. Oh.
Yeah. All right. But of course, again, you know, actually that's a good way for me to talk about imperfections. Okay, so let's just briefly talk about imperfections in imaging. Okay, since we are talking about perfect imaging, we understand what it takes to make a perfect imaging now. We need all the rays to have the same amount of time going from the object to the image. But what is it? Why don't we get perfect imaging all the time? Why do we get imperfections? Okay, so the first reason is something that we've already discussed in an earlier lecture, which is scattering. In particular, I talked about all of these surfaces, whether it's a lens, whether it's a mirror, as perfect reflectors or extremely smooth surfaces through which the rays are propagating without any scattering. But of course, as we look at a microscopic level, when we look at, say, a mirror surface, for example, and I have a ray that's coming here, yes, you get the perfect specular reflection. Remember, we talked about the specular reflection beam, which satisfies the law of reflection, but we also get some other ghost reflections or diffuse reflections. Okay, so the first way in which we can get imperfections is that some of the rays, even though they are, by the law of reflection, they should only go in one direction. There are some rays, some amount of energy, if you like, that's lost to scattering. Okay. Similarly, inside a smooth, if I take some lens, for example, I made a lens, maybe it's a thick lens like this one. Inside this lens, there's some imperfections. So little points where the glass is not perfectly smooth, maybe even the surface that has been ground down. Usually you're taking glass and you're grinding it and polishing it. Maybe the surface isn't perfectly, smooth. So then you're going to get, again, scattering. The body of the glass may not exactly be uniformly smooth. There may be like impurities and defects inside it, which cause scattering of the light. In fact, I think I mentioned this to you before, that the reason that optical fibers became a viable technology is that the scientists discovered how to make extremely smooth glass fibers with almost no imperfections inside them and going on for like kilometers, right? I mean, that's a huge achievement. That's why they got a Nobel Prize, because that's a very hard problem to solve. Okay. All right. So that's scattering. Sorry. Start playing some. That is scattering. Okay. The next one, which is known in the optics community as aberrations. Well, what this is due to, as I just told you, first of all, we need a paraboloidal mirror, right? For example, for perfect reflection. It'll turn out, as I'll show you in a minute, that for like these, for a refractive surface, we need kind of ellipsoidal or even hyperboloidal mirrors, depending on the geometry of these mirrors. Okay. Well, it turns out that it's very hard to make these surfaces. Okay. For example, paraboloidal mirrors, it's hard to make them because you need very clever machining tools to like turn a metal surface into a perfectly smooth parabola. Okay. Or parabola. And similarly with the glass, making a glass surface into a aspherical, these are often referred to as aspherical surfaces because they're ellipsoidal, they're hyperboloidal, they're parabolic. These are not spheres. Okay. And it turns out for centuries, the glass people, glass blowers and like glass grinding shops, machining shops, they knew how to make very smooth spherical surfaces by grinding them in like a little spherical hole. They could make the glass very, very smooth by using various techniques. Basically, it's like the idea is you take like a glass surface and then you put it in like a little, a holder which has been machined in a metal, and then you like grind it with some slurry. Okay, and the idea, of course, there is everything you move like sort of concentric and circular, and so that makes everything very smooth and circular, but not ellipsoidal, hyperboloidal, paraboloidal. Those are difficult surfaces to make. So we inevitably end up with a surface that are, in fact, for the longest time, even now, all the lenses that you can buy typically from a glass shop are going to be spherical lenses. They have spherical surfaces on both sides, which, as I just said, is not the ideal surface for imaging. Okay, so that gives rise to so-called aberration. So they're a result simply of like our inability to match that perfect Cartesian surface, the one that gives us the ideal imaging condition. Okay, and the last one, which somebody briefly was asking me about, is diffraction. Okay, so what is this due to? Well, I erased it, but I told you that for perfect imaging or conjugate or stigmatic imaging, where O and I are the conjugate points, every ray that leaves O must arrive at I. Okay, which means, of course, there are an infinite set of rays extending over all of space. Okay, and I'm demanding that every single such ray from O arrive at the point I, which means I have to capture an infinite number of rays, right? Or all of the energy coming from O into the point I. But of course, our optical systems are going to be finite in dimension. Okay. What that means is because we can only capture a finite number of rays at the edges of our optical system, the wave nature of light is going to start coming into play. It's going to see that abruptly we went from having certain shape or certain behavior like refraction or reflection. Suddenly now there's no surface, right? So at that boundary, which usually, you take a lens or you take a mirror, there's going to be a boundary, okay? And that boundary is sharp enough, effectively, that usually there's going to be some wave nature that occurs, and you get diffraction, as we call it, is due to the presence of this finite boundary, okay? And that finite boundary gives rise to wave optics, or wave nature of light, is from the wave nature of light. So for most situations, this diffraction will set a limit on how good of a image you can create, how much of the energy from the object point gets concentrated into the image point. It's never going to be a perfect point. It's always going to be a region around that perfect point in which the energy appears. And so that gives rise to a loss of resolution. You can't make infinitely sharp images because of this. Okay. All right, so these are all some various aspects of imaging systems that we've discovered. As I'll try to derive for you, or at least at the very least, I'll write down an equation for like the Cartesian oval, but we won't get into details. Obviously, that's like just a lot of math. Okay, so I'll write down the expression for it in a minute, but before I do that, do we have any questions on what I've said so far? Okay, so before I do more math, let us do a little bit of fun things with format sprints. Okay. The first thing that we can think about, or at least one of the ways in which format sprints will manifest itself in regular life, so to speak, is if you think about what happens when you're driving down a hot road. Okay, so it's a very, very hot summer day. You're driving down this road, and as you drive, you observe, I'm sure you've all seen this phenomena, that in the distance, there'll appear like there's some shimmering of the road, almost like there's water on the road, right? Everybody's seen this, right? Okay. So what is that? What is going on with that? Well, and also similarly, the people who travel in the desert, they observe mirages. Okay, so they may see suddenly floating in the sky. It looks like it's close to them, is like a city or an oasis. Actually, is a more common thing where people start seeing like water. They say, "Oh, there's a water over there. There's an oasis. I better run and get to it because I'm so thirsty." And then, of course, they end up running and running, losing all their energy. Then basically, vultures come in. Okay, so what's happening here? Okay, so here's a person. Okay, on maybe they're walking on a hot sand, or there's a hot road surface or sand in the desert. Okay. And the air right above that sand, obviously, or road is very hot. Okay. Then by the ideal gas law, you can easily ask yourself what happens to the density of the air. That's going to be less. Okay. The hot air has lower density. Okay. You can easily show that by just taking the ideal gas law, for example. Okay. And low density also means, therefore, lower refractive index, because the index of refraction is kind of related to the density of the material. The more dense it is, it deviates more from just being vacuum one. Okay. So the hot air in the middle, or down here, sorry, at the bottom, is going to be basically much lower index than the cold air, which is higher up, which is, now having a higher index. Okay. So now let's think about the sky, or maybe there's a city over here at a height, or there's even like an oasis at a different, or some water or something, but mostly it's the sky that gives rise to this phenomenon. Okay. So rays of light, as we know, the molecules in the air, in the upper atmosphere, are scattering the blue light out. And so all of this blue light is propagating downward like this. And of course, most of the rays from the blue light, which are over here, will never make it to this person, right? They may be looking up at the sky, and they'll get some rays of light coming from the sky, and that clearly goes into the sky, so they don't get fooled by those rays. But some of these rays that are coming at a low angle, perhaps from some distant object or from a distant part of the sky, as they approach the bottom, right, they see that, but they can actually lower the time that it takes them by going downward and then coming up. Okay. Or you can also argue on the basis of like total internal reflection, like you're going from high density or high index to low index, so you're going to bend like this. So essentially what's happening is that this person, instead of seeing the sky up over here, if they project the rays of light backward, they're going to see something that looks like a blue region on the ground, which is the sky basically reflected into the surface of the road or the sand, etc. So that's one way in which a mirage can appear. Another similar phenomena is actually something that you may or may not be aware of, that actually when you observe the sun at a sunrise or a sunset, the sun has already set, or has not risen yet. Okay. So this is interesting, right? So actually what you're observing is the apparent position of the sun, not the real position of the sun. Why is this? Well, again, it's the same phenomena. So let's say we have a person here, okay, on the earth. And this is, of course, the curvature of the earth, which sets the horizon. Okay. So the person can't see any rays. So let's say the sun is over here. Okay. Then rays of the sun are blocked by the ground, the curvature of the earth. So the sun has either already set or has not yet risen, okay, in this case. But again, the same phenomena, the atmosphere has gradient of density, as we all know. So lower down is more dense atmosphere, and higher up is the upper atmosphere, which is much thinner. Well, again, there are rays from the sun which can minimize their optical path by going up first and bending back down to reach the person's eyes. Okay. Again, you can argue about this through total internal reflection or something if you like. And so again, if we ask this person where the sun is, they'll project these rays backward, and the sun, the apparent position of the sun, will actually appear to be higher up in the sky. This effect can be about half a degree. So even though the sun hasn't risen yet, in some real sense, because it's not over the horizon yet, to this person, it'll look like the sun has already risen. Okay, so a few minutes ahead of that actual time. Okay. The same, of course, the other direction when the sun is setting. So these are a couple phenomena. There are lots of other phenomena like this that one can think about using Fermat's principle to argue about what the optical effects are going to be. But I just wanted to point those two out. Okay, so now I will talk to you about Cartesian imaging on Cartesian surfaces, which is just really an extension of what I just did for the paraboloidal mirror, but with the refraction instead of reflection. Show a set of coordinates, right? Always important. Okay, so again, I set up our object point O. And then I have, so here I guess I treat the coordinates correctly. Well, whatever. I should fix that other one. So here's my origin, which is where the object is located. Okay. And now I have the difference here now is that this surface is a transparent medium with some refractive index. So in here, if you like, this medium extends to infinity over here on the right hand side, and it has some refractive index, which I call n sub I, which is for imaging medium. Okay, so this is the medium in which the image is formed. Okay, and we can now ask what happens to rays that go either like this and get imaged onto the image point over here. Okay, and of course, this point over here, which is P, has the coordinates x, comma, y. Okay, this is the x-axis and the y-axis. Y and x. Okay, so and also let's assume that the object part, which is the object, is in a medium of refractive index n0. Typically, for in the lab, this would be, for example, in air, and then this surface over here might be the first surface of a glass lens, a convex or concave lens. Okay, so I want, let's call this distance d naught, this distance di, and then this distance to where the surface of the lens intersects the ray from O to I, the direct straight line ray. This distance again, at this point here is again called the vertex V. Okay, and the distance from O to V is always denoted by S naught, or SO. I guess I end up calling it S naught, but it's really the object distance, so SO. And similarly, we have an image distance from the vertex to the image point, which is SI. Okay. And as I said, this medium over here has refractive index n naught. This medium has refractive index n. So by the same Fermat's principle, now I can simply write down the equation that defines the surface. I just equate the ray, the optical path length, basically, that it takes, or the time that it takes for this ray to go from here to P and back down to I. So that's OP plus PI, which is N naught D naught plus NI DI, must be equal to the straight line path, which is N naught S naught plus NI SM. Okay. And that's all I need to write down an equation for the surface of this refractor. Okay, this perfect refractor, just like this is the parabolic mirror was a perfect reflector. This is a perfect refractor. Okay, it creates a perfect image of the point O in the point I through refraction. Okay, and so I can write down the equation. Not that we will try to solve this exactly. Okay, so it's just this plus Ni times y squared plus S naught plus S minus x the whole squared square root is equal to N naught S naught. Again, as I said, I'm not going to solve this exactly, but this is the equation, and this is called a Cartesian oval or a Cartesian surface. Write it down. Cartesian . The Cartesian oval or Cartesian surface guarantees perfect imaging. Okay, and actually, if you looked in your book, you could look at also examples where either S naught goes to infinity or SI goes to infinity. Okay, those are situations. What do I mean by the image point going to infinity? Well, it means now that the rays of light have to travel parallel to each other, right? They'll all be parallel to each other, so the image will be formed at infinity. Basically, the image point is essentially so far away that it looks like the rays going outward from the system are all just parallel to each other. Similarly, if the object point is at infinity, that's just like the earlier situation I drew for the paraboloidal mirror, where when the object was at infinity, like a distant star, then the rays of light coming in from the object are all parallel to each other. So that's S naught going to infinity. Okay. And you can see those situations, the answers are usually they're like hyperboloidal or paraboloidal, again, surfaces for the refracting surface. Okay, so as I already mentioned, so first of all, that it's very difficult to make these surfaces. These are often confusingly referred to as A-spheres. Okay, well, they are aspherical, so they're A-spheres. So and the fact that that they're A-spheres makes them difficult to create exactly, to grind exactly. So in principle, then although we know that that's the correct surface to make, it's hard to make them. So we end up with spherical surfaces. And so we're going to get aberrations, as I mentioned. In fact, confusingly, one of those aberrations is called spherical aberration, which isn't very helpful because it sounds like, it's due to the fact that the thing is a sphere, but in fact, it's because it's not a perfect A-sphere. It's not a perfect Cartesian surface. The spherical surface is giving rise to, it should really be called aspherical aberration. The fact that it's not a perfect A-sphere or a perfect Cartesian surface. Okay, so by the way, before I go on, does anybody, let's say I now wanted to make an image from the point P1 to a point P2, okay? All right, so I want a perfect image, and I want to do it by using a reflector, okay? Which maybe captures all of the energy or maybe even half the energy or something. So what I mean by this is a reflector, and now the point P1 is at infinity, so it's not a paraboloidal mirror, but it's at a finite distance. So I want to make the rays all have the same distance from P1 to P2, okay, while bouncing off this surface. So the point C lives on a surface which is on a reflecting material. And now P1 to P2, every point on the surface must be the same distance away from P1 and P2, right? Meaning this R1 and R2, if these are the distances, R1 plus R2 must be a constant for every point on that surface. Do you know what such a surface might be called? Have you seen such a surface? Maybe you've played with these in like high school.
Yeah, so about the properties of the elliptic shape.
Elliptical shapes, exactly. So if you've ever played with this, you take two rubber bands, attach them to like two pins, and then, or string or something, attach them to two pins and a pencil. And if you sketched it, then that would be the shape, that would be an ellipse. Okay? So that's exactly the same geometry over here. So if you want like, perfect imaging from one point to another with a reflecting surface, you would make an elliptical mirror. Okay. All right. So now let me, in the last few minutes, quickly set up the problem of again, we're going to skip through a lot of the details of the math because I can always post a little video explaining it if you like. But I just want to tell you about how the spherical surface imaging works. Okay. That will help us to set up the equation for the lens. So now I go from the point S to the point P. Okay. And again, I have my surface over here. But now this surface is no longer an A-sphere, it's a spherical surface. So because it's a spherical surface, it has a center, C, from which every point on the surface has the same distance R, the radius of curvature of this surface. Okay. So that's the radius of curvature. And now if I take a point, a ray that goes from here up to here, remember a ray, the radius of a surface makes a 90-degree angle to the tangent to that surface. Okay, so this is the normal to the surface at this point. That is, the radius is the normal to the spherical surface, which is pretty clear. And so this angle here is the incident angle, which is theta I. Then similarly, of course, it undergoes refraction and hits the point P, and therefore this angle is theta T, transmitted angle or the refracted angle. Okay. And again, this medium over here has refractive index Ni, N naught. Well, I guess I called it N1. So refractive index 1. And here has refractive index N2. Okay. All right. So this angle over here, since it's a sphere, right? All we need to describe the coordinates of a point on a sphere are the radius, the latitude, which is sort of the angle above the equator of the sphere, right? And of course, the azimuth, which would be the angle around the sphere, which would be like the longitude, okay? Well, since we have spherical symmetry in this problem, we don't worry about the longitude or the azimuthal angle. We only worry about this angle relative to the equator of this vertical of the central line. So that is this angle phi over here. Okay, that's this angle phi, which is the angle that the point P, which is where the refraction is happening, makes with respect to the central point C. Okay. All right. So now again, we can use Fermat's principle and write down the optical path length. So we want the optical path length of this array, which goes from here up to here and back down here. So I call this distance L naught, this distance Li. So the optical path length is simply N naught L naught plus Ni L naught. And this must be a constant, and that must be equal to the total length from here up to here, right? From S to P. But more importantly, what I'm trying to point out is because this must be a constant, right? It's the same for all the rays. We can take if I call this the OPL, if I take the derivative of the OPL with respect to the angle phi, if I can express the optical path length, this optical path length in terms of phi and these other parameters like R and the refractive index, then by taking the derivative with respect to phi and equating it to 0, I'll get an expression for the relationship between the distances from the between this S and the vertex and S and the P and the vertex, and also the angle and the radius and so on. So I'm not going to go through that math. I'll put a little video if you like to show the math, but we can then finally end up with an equation. Okay, and that equation is given here as N1 divided by L naught plus N2 divided by Li is equal to 1 over R. Again, this distance from S to B I call as S naught, and this distance from B to P, sorry, I call as SI. Okay, object and image distances. So I get this expression here. I'm skipping all the math details. It's pretty basically just finding those distances and taking the derivative, which is not super important for what I'm trying to explain. As I said, I'll put a little video later for that. Yeah, so again, this expression is somewhat helpful, but it's still in terms of L naught and Li, which are dependent on this angle phi. So it doesn't help us a whole lot, although it's nice to have this expression. So we take a further approximation. Again, skipping all the math details. We assume that the angles phi, meaning the point location P, is not very far from the axis. And this is called the paraxial approximation. Just one more minute and I'll write down the final answer and then we can. Phi is small. The angles of the rays are not very large. And in that case, everything simplifies a whole lot more to a much simpler looking equation. And this is an important equation for you to know and to remember. Okay. So that is the paraxial approximation through refraction at a spherical surface. So, and this is done in the first order. Basically, what I'm doing is I'll express everything in terms of angle, cosines and sines. I'll expand out the cosines and sines and drop everything but the first term. That's how I got this expression. Okay. So when you see the video, you'll see all of that in more detail, but this is the final sort of expression for the first order theory. Okay. So that basically is called the paraxial approximation, or also it's sometimes called the Gaussian approximation. All right, I'm going to stop there and we'll continue this in the next class.